Today I'm going to talk about Lenz law. So what is Lenz law? Well, basically it's a law that's worried about maintaining the status quo. In other words, a system always wants to maintain a status quo. And when I mean system, I'm really talking about a coil in this situation. Another thing I want to point out, I'm going to be using different terms at times. So I could use the word loop, and all that means is really just one single loop of wire. I could use the word solenoid, and that's more like this or this, where you have lots and lots of wire wrapped around something. I could also use the word coil as a general term. But no matter what term I use, all of them obey Lenz law. Now, here's the thing about this. Because of the virus, I really can't use the solenoid I usually use for this demonstration. This solenoid, unfortunately, doesn't have enough turns. And what that means, we'll find out, is that a device like this, a galvanometer, would not be able to pick up any current or voltage. So I had to create another solenoid. Here it is. So this has more turns, has about 63 turns. And another thing we'll find out is I've indicated the direction of the turn, and you'll find out why we're doing that shortly. Also, I am measuring the current that's going through this coil. And one of the key things to note, there is no battery attached to this. This is just a coil wire in which I attach current probes. And I will be using my vernier current probe to do this. And there's something else that we're going to have to look at. So I'm done with this. And that is, I'm going to use a magnet. So this is one of those super magnets. And one of the things I need to know is, what end of the magnet is this? In other words, what's its polarity? Well, I have a compass here. And according to the pole rule, opposites attract. Now, just so you know, on a compass, the red end, you can't see it, the red end represents north, the white end, south. So therefore, this pointy end of my magnet is a north pole. So the question is, what's going to take place when we perform Lenz law? And let me kind of explain it this way. It turns out that a coil has special properties. And one of those properties is, under the right conditions, you can generate a magnetic field. Or in other words, it can generate a magnetic field. But when it does that, it will also create a voltage difference across its ends, and consequently, there'll be a flow of current through the coil. But how do we accomplish this? It turns out that you need to have a moving magnetic field, a changing magnetic field. So if I take a magnet like this and I move it up and down through the hole, the magnetic field is changing. Why is it changing? Because when you're far away from the magnet, and apparently this one's getting stuck to my table, the fields go out like this. So when you're over here from the magnet, the fields are more spread out. But when you're here, closer to the end, the fields are closer together. So the magnetic field is more intense here and less intense here. One key thing to note is, if I just simply held this magnet over this coil, nothing will happen. It has to be a changing magnetic field in order to cause a current to flow through this wire. So I'm going to take this, go up and down, up and down, up and down. How am I actually going to measure this? Well, I have my vernier, okay, right here. Let me make sure I'm still centered. Okay, I am. And let me take this here a little bit. So this time it's a little bit crowded. Okay. And what I'm going to do is I'm going to go ahead and start a new run. Nope, I'm going to disregard that. And watch what happens. When I go in, there's a little peak. If I take it out, there's another peak, but in the opposite direction. In, out. In, out. Okay, now you can see it better. So the question is, what happened here? Well, it's picking up a current, and in this case, when I took my magnet and I had it approaching the coil, it generated a positive current. Or in other words, I really should say, it generated a current that came through this terminal. The peak going down, that represents me moving the magnet away, and that's when the current went through this. Now, when I talk about current, of course, I'm talking about conventional current, the right-hand rule. So, how does this relate to Lenz's law? Well, let me take this for a second and put it on its side like this so you can see the coils. Here's what we have initially. Imagine that this here, this longer wooden stick, is representing this magnet here. Okay? And I'm going to put this a little bit closer up here so the people in the cheap seats can see it. All right, there we go. All right, so that there, right here, stick here, whoops, is going to represent, this is going to represent that. Okay. Now, if the magnet here just stays right here, okay, and I measured it on my machine, nothing would happen. The magnet has to be moving. But you might remember when I started to insert the magnet this way, we've got a current flowing. And the question is, why? Well, it's Lenz's law. And Lenz's law says it wants to maintain the status quo. So what do we mean by status quo? It simply means that if my system starts off like this, it wants to stay like this. It doesn't want anything to change. So imagine this. I'm going to start taking that north magnet, bringing it into this coil. This coil is going to act in such a way to say, I don't want this bar magnet near me. So it turns out that this coil can generate a current, and when it generates a current, it generates a magnetic field in that coil. How do I prevent the North Pole of this magnet coming in? Well, the coil, would have to generate a North Pole, because this way it would be repulsion. I'm trying to keep it out. Now, here's one thing to note. This is a real magnet. Okay, so whether anything is moving or not, it exists. This is a temporary magnet that the coil generates while this is moving. Once this stops moving, this disappears. So if you're trying to bring the two things together, there's going to be a repulsion. That's what Lenz's law says. It doesn't want to be brought together. Get back to where you were. What about if I did it going to the South Pole? Well, same thing's going to happen. If I bring that South Pole this way, Lenz's law says, hey, I don't want you to come any closer. It will generate a current that will generate a magnetic field that will be, a magnetic field that will be like this bar magnet here, where this is another South Pole. trying to repel this larger magnet. So here's the first rule. If the two objects in our system, which in this case is a coil and a magnet, if they're coming together, then there's going to be a magnetic repulsive force. And that can only happen if both of these on this side have the same polarity. And that's when they're coming together, because Lenz's law doesn't want them to come together. But there's a second one. What if I took this North Pole and I had it here, okay? It's not moving. There would be no current generated, okay? You wouldn't see anything happening. But now I decide to move it away. Well, now Lenz's law says, wait, I don't want you to leave. I want you to stay where you were. It will generate a current through this coil that will generate or produce an attractive magnetic force. So in this case, it would have to be a south pole. You try to leave, I want you to come back. Here I am. If you stop moving right there, this disappears. It's only when this is moving that this appears or is generated. What about, hey, you're a south pole, okay? You move the magnet away. Well, Lenz's law says, don't do that. I don't want you to do that. So it will generate a north pole on this end of the magnet. Of the coil. It's trying to attract it back this way. So here's what we have. This is our second rule. If the two objects in our system, the coil and the magnet, are moving away, there's going to be a magnetic attractive force between them. So if this is north, then this has to be south, and vice versa. I should also point out this. So far I've been moving the bar magnet, but I don't have to. I could hold the bar magnet here and move the coil. It would still be the same effect as me moving the magnet this way. So you've got this little effect here, and actually Lenz's law is very important in something that we call a generator. If you've ever taken apart a motor, little kid's motor, or if you ever go to a plant and you see those big generators, they're basically a lot of copper wire wrapped around some type of rotor, and then around it are basically permanent, not bar magnets, but permanent magnets. In other words, in a generator, it's not the magnet that's moving, it is the coil. So when the coil moves like this, woo, woo, bingo, hey, you're going to generate a voltage, which in turn will generate a current. You've just generated electricity. Real quick example of this also is, if you've ever seen one of those flashlights that you shake, and you can see in it, and you might notice there's like this, there's this like goldish or reddish tinted wire. That's actually a solenoid, okay, like this coil here. And then the silver thing that's going up and down is a bar magnet. And that's how you can shake it, and goes in and out, and you can generate electricity. There is still one other thing I wanted to talk about, and that was this. I proved to you somewhere, here it is. I proved to you by using a compass that this was a North Pole magnet. Okay, let me make sure I'm still on track here. Okay. But how do I actually know the polarity? How do I actually know the polarity of this solenoid? Well, let's look at this. You might remember that what I first did was I did something like this. First thing I did was I took my little bar magnet and I put it closer, and we got this peak going up. Okay, this is current that's going into the red terminal here. If it's going down, it's going into the black terminal. But how do I know that for sure? And how do I know the polarity? Well, remember how I showed you how the wire was wrapped like this. It turns out that and I got to get my fingers straight here. Yeah, this wire is going like this. Okay, see how I got my fingers this way? Now, the current is going around, we're going around, and it comes out here, positive. But if I wrap the fingers of my right hand, remember that right hand rule? Put my fingers around here in the direction of the current, look where my thumb is pointing, North Pole. When I took the magnet out, this went down. Well, why did it go down? Because the solenoid now, by Lenz law, it doesn't want it to leave. So it generates a south pole. Well, how do you get a south pole? Well, this time it had the reverse direction in my coil. So it went this way because this end here would be, I'm trying to do it with my hand here, that would be the North Pole. So the rotation would be this way. It would come out this wire to the negative terminal there. Okay. So there is a homework problem in which I ask you to pretend like, let's try to get this again, okay. Pretend like here's a loop of wire right here, and hey, you're over here. Let's make this you. You're over here, and you're looking at this. So this could be you looking straight on this way. And so here's the magnet. And I'm going to put it this way. Okay, so we start off with something like this. Now, here's what we want to know. Here's your loop. Here's your bar magnet that actually exists. This is you, the observer. And also you should know, this is the top view. This would also be you, the observer. And I say, hey, let's move the south pole of that bar magnet away. The question is, what will the coil try to do? Does it want to attract or does it want to repel the bar magnet? According to Lenz law, it wants everything to stay the same. So it wants that bar magnet back here. And the only way it can do it is if it generates a magnetic North Pole, because an attractive force will bring it back, right? Now, if this is a North Pole on the coil, okay, on the coil, then my thumb would be pointing this way, okay? See that there? Something to note, if my thumb's pointing that way, then you would be seeing the South Pole on this side of the coil. Not paying attention to this, but we're looking at the coil. North Pole here, South Pole here you'd be looking at. By the way, remember that thing how we took our loop and I pivoted on my little finger? If I pivot this down, boom, look at the rotation we get. It is a counterclockwise rotation, just like this. Okay. So let me give you one other one. Okay, here we go. What if I had the North Pole here? So you start off, here's the coil, here's the bar magnet, North Pole there. Okay, you're looking at that. Now, the bar magnet is going to be moved away. That goes, oh, hang on. You know what? Let me do another one. Yeah, because I think that was the one on homework, so I'm not going to do that. So let's do it this way. Let's make this the South Pole, and it happens to be here, and all of a sudden now, by the way, right now, nothing's happening, so there'd be no current, no magnetic field in that coil. But if I bring it together, if I bring them together like that, something's going to happen to that coil. By Lenz law, that coil would say, I don't want you near me. Get away from me. Well, the only way it can make this bar magnet go back is if it generates a South Pole at this end. Then it would be repelling that. Now, I want you to think about this, okay? If that is the South Pole, now we're going to focus in on the coil, That's the South Pole. Here's the North Pole. Look at how my fingers curl. So if you're looking this way, you're seeing in the coil a North Pole. If I once again rotate it down, like what we learned in our another video, if I rotate this down, notice my thumb would be going into the board, or in other words, it'd be a situation like this. Magnetic field going into the board. The current in that coil, we would say it is clockwise. And that's it.